All right, in this video we're going to talk about the Section 5 differentiability and continuity. So we're still in Chapter 1. So when you think about differentiability, I want you to think about the derivative. So I'm just going to put the symbol here for derivative. Let's see if I can get that back up. Okay, so I'm just going to put f prime of x. Okay, and for continuity, I'm going to write no gaps. All right, then we have some notes to fill in. So it said that in sections 1, 3, and 1, 4, we define differentiability as the ability to take a first derivative of f of x at some point. So if a limit exists at x equals a, then we said the function is differentiable. So on this line, write in the word differentiable. And if a limit does not exist at x equals a, then the function is not differentiable. All right, so that seems pretty self-explanatory. Okay, next we're going to look at some graphs. So I'm going to do this on the next page of notes. Okay, focusing just on these sketches, we're going to talk about differentiability in terms of the geometry of it, and that's something that we have not yet talked about. So in order to be differentiable in terms of the geometry of a function, you have to be able to draw a tangent line there. So there's a couple of places that cannot happen. So right here, when you have a point, that's considered not differentiable. Where you have this little shape that looks like kind of the peak of a wave, it's called a cusp. That's considered not differentiable. Where you have a corner, that is not differentiable. And where a tangent line will be a vertical line, that's not differentiable. So these are the geometric exceptions to the rule of differentiability. So all of these functions are continuous, but they're not differentiable because of the features that are embedded in the function. So vertical line, corner, cusp, and point are all geometric features that make the function not differentiable at the occurrence of those events. So let's talk about continuity on the next page of notes. Okay, for a function to be continuous, the easiest definition of that is to think about drawing the function. If you have to pick up your pencil in order to draw it, your function is not continuous. So look at the two functions that we have here. So the first one is a step function, and step functions have to be drawn picking up your pencil. So therefore, it is not differentiable wherever you have a step. Piecewise functions clearly need to be drawn picking up your pencil. So therefore, where you have the break, your function is not continuous. If a function is not continuous, you cannot take the derivative at the point of the break. So for the second function, you can take the derivative right here where I'm drawing my little arrow, but you cannot take the derivative right here at the break. All right, so that's the idea of continuity. So what we want to pull together at this point is the relationship between differentiability and continuity, and that's summarized for you right here. So the relationship is as follows. If some function is differentiable at x equals a, then it's continuous. Okay, so if it's differentiable at a certain x equal a, it has to be continuous there. However, so this big but in the bold, a function could be continuous at x equal a, but not differentiable. So think about your piecewise function, think about your cusp, your corner, your vertical line, and your point on the first page of the notes. All of those functions were continuous, but they were not differentiable at that point. Okay, then they give us another little definition. This is the limit definition of continuity. So a function f of x is continuous at x equal a, provided that the following limit relation holds. So the limit as x approaches a of f of x has to equal f of a. So think about that. Think about that in terms of the piecewise function. and you see that that's not true. So therefore, that's not continuous. So note, special important note, in order to take a derivative of a function, at some point, the function must be differentiable and thus continuous, and without points or vertical lines, at that particular x value. So to practice this, I have a homework sheet. We're going to do the following problems that are listed here. Problem 20 and 21 is not in your textbook, but it's on the worksheet. So that's the end of the notes for this section 1.5. So it's very short, but there's some important material in there. You want to know the difference and the similarities between differentiability and continuity.